we derived the differential energy balance equation in terms of total energy, and then through a series of steps we expressed in terms of temperature, and we realized that we have the components of heat flux vector which needs to be expressed in terms of temperature gradient to close the system of equations, and that is what we are going to discuss in this lecture. And first we are going to discuss about the Fourier's law of heat conduction, which will close the system of equations, and then simplifications of the differential energy balance to forms which are usually applied. Okay. Before we discuss the Fourier's law of heat conduction, let us have few recall slides on Newton's law of viscosity. Now, if we recall, we interpreted tau in two different ways. First was in terms of viscous stress, and we expressed the Newton's law of viscosity as the viscous stress proportional to the velocity gradient, and the constant of proportionality is the viscosity. Then when we came to the transport phenomena part of the course, when we discussed momentum transport, we viewed tau as molecular momentum flux and expressed the Newton's law of viscosity as the molecular momentum flux proportional to the velocity gradient. To take care of sign convention, we introduced a minus sign. The constant of proportionality was the viscosity. Now, this interpretation of tau as molecular momentum flux is what is relevant for present discussion. Remember, when we discussed the two viewpoints of tau, we said one advantage of interpreting tau as molecular momentum flux is that we can discuss the analogy between molecular momentum flux, molecular heat flux, and then species flux, and that is what we will see now. So, the discussion which follows now for relating heat flux and temperature gradient will be analogous to our discussion on relating molecular momentum flux and velocity gradient. It will not be similar to the discussion on relating viscous stress and then velocity gradient. Okay. That is why we interpreted, that is one of the reasons for interpreting tau as molecular momentum flux. Okay. Let us see how they are analogous. So, we will discuss the Fourier's law of heat conduction analogous to the discussion we had on Newton's law of viscosity, where we interpreted tau as molecular momentum flux. Now, what we will do is consider two plates, okay, which are parallel to each other and whose area is A. So, when I say area, I mean this area, okay, this area. We have a plate here, another plate here, and a slab of solid material is located between the two large parallel plates. The solid material is shown here. So, we have two plates and then we have a solid material between them. What is the difference? So far we have seen this configuration as two parallel plates with fluid flowing between them. Instead of that, now we have the two parallel plates, we have a solid slab between the two plates. Okay. So, we will take the condition where the two plates are maintained at two different temperatures. The top plate is maintained at T naught, that is a temperature here, and then the bottom plate is maintained at temperature T1, which is higher than T naught. Okay. So, this plate at T naught, this plate at T1. Now, a constant rate of heat flow is required to maintain the temperature difference. Okay. Constant rate of heat flow is required from the region of higher temperature to the region of low temperature, so that this temperature difference is maintained. Okay. Now, it is experimentally found that is a key word here, experimentally found that for small delta T, let us say differing by let us say 1 degrees or 0.1 degree centigrade, what is experimentally found is that the rate of heat flow per unit area through which heat flows, which we call as heat flux, because it is rate of heat flow per area, it is heat flux, that is found to be proportional to the temperature decrease over distance y, and that is what is shown here. So, heat flux proportional to the temperature decrease over distance y, and the constant of proportionality is the thermal conductivity of the slab material. Now, for illustration we have taken a solid slab between the two plates. When we discussed Newton's law of viscosity, we took a liquid or a fluid between the two plates. What is the reason why we have taken solid here? Remember, conduction takes place in solids, liquids and gases as well. Now, what is the reason for considering solid in the present case for discussing Fourier's law of heat conduction? Let us say if you have taken a liquid or a gas between the two plates, what will happen? This plate is at a higher temperature, this plate is at a lower temperature. So, the fluid here will be at a higher temperature, it will have a lower density, and the fluid here will be at a lower temperature, will have a higher density. So, which means that this fluid will move here and there will be movement of liquid in the region which we are considering, which will add to the complexity, which we call as convection. So, to eliminate convection only, we have considered a solid slab of solid material between the two plates. Further, if you have a fluid between the two plates, there can be heat transfer because of radiation. To eliminate radiation, of course, radiation plays a significant role only at high temperatures, but to eliminate radiation only we have considered a slab of solid material between the two plates. Okay. So, we considered a solid material between the two plates instead of a fluid, so that we can eliminate convection and radiation. So, putting it the other way, this equation or this experimental observation that rate of heat flow per area is proportional to temperature decrease over distance is valid for liquid and gas also, certainly if convection and radiation are eliminated. Okay. So, that should be kept in mind. Okay. We have seen this expression in the previous slide, which says that the heat flux by conduction is proportional to temperature gradient. So, let us start using more formal words. This is heat flux, this temperature gradient. So, heat flux by conduction is proportional to temperature gradient. Now, how do we express this in differential form? Okay, that is expressing in terms of a difference. So, left hand side we have q y, why is that it is q y? The example which I have considered, we have x is along horizontal direction, y is along the vertical direction, and flow of heat takes place in the y direction from the lower plate to the top plate, and that is why this is heat flux in the y direction. And right hand side, if you express this, we have K dou T by dou y. Now, we know that heat flows from a region of higher temperature to a region of lower temperature. So, in this case the direction of heat flow is along this direction, along the positive y axis, but we know that it is from a higher temperature to a lower temperature, which means it is along the direction of negative temperature gradient. So, if you substitute here, what will happen? Dou T by dou y is negative and heat flux will be negative, but whenever something flows, let it be velocity or heat flow, I want it to have a positive value when it flows along the positive y axis. So, to achieve that sign convention, what is that? Heat flux to be positive when heat flows along positive y direction. In the present case, if you leave this expression as such, Q y will be negative, but heat flow will be happening along positive y axis, but I want it to be positive when heat is flowing along positive y axis. So, I include a negative sign. So, Q y is equal to minus K dou T by dou y. Now, what happens if you apply this equation for the present case? Dou T by dou y is negative, Q y is positive and it is flowing along the positive y axis, okay. And that is the Fourier's law of heat conduction, or the one dimensional form of the Fourier's law of heat conduction. What we have discussed is once again analogous to what we discussed under the momentum transport. To begin with, we had the molecular momentum flux proportional to the velocity gradient alone. There again we wanted the momentum flux to be positive when there is transport of momentum along the positive axis. So, we included a negative sign. Of course, there it was momentum flux transported, molecular momentum flux transported from a region of higher velocity to lower velocity, but otherwise the reason for adding negative sign in both the cases is analogous. Okay. We will express the Fourier's law of heat conduction in the 3 dimensional form. We have this expression in the x direction, we will just extend, we will write similar expressions for the y direction and the z direction. So, heat flux in a particular direction is proportional to the temperature gradient in that direction. We can express these 3 equations in the vector form, which is very compact. At left hand side we have q vector, right hand side we have minus k gradient of t, and q vector we have seen this some time back is q x I, q I j, q z k. Of course, we know gradient of t is dou t by dou x I, dou t by dou y j, dou t by dou z k. So, the left hand side is the q vector, right hand side we have minus of gradient of temperature. Of course, thermal conductivity is the material property. Now, if you look at this expression, I have used the same thermal conductivity in all the 3 directions. We have qx, qy, qz. So, there is a direction attached to the left side. I have also attached a direction to the gradient of temperature dou t by dou x, dou t by dou y, dou t by dou z, but k has been taken as same along the 3 directions, and that we know defines the isotropic material. So, this Fourier's law of heat conduction which we are discussing is applicable for a homogeneous isotropic material. Why is it isotropic? At the same point the thermal conductivity is taken to be same in all the 3 directions. Okay. This may not be applicable for all the materials, as we have seen earlier. Wood is a good example for non-isotropic material. Thermal conductivity will differ depending on the direction, and this is the second constitutive relation which we are coming across. The first one is the Newton's law of viscosity. This is the second constitutive relation, which is the Fourier's law of heat conduction. As a quick recap, what is a constitutive relation? Relate unknown variables in terms of known variables, What is unknown variable here? The heat flux, known variable temperature, and this relationship closes the conservation equation energy balance here. Once again it is experimentally obtained, we are not deriving it, we only stated that, and then describe behavior of a material. There it was a mechanical behavior, but now it is a thermal behavior. It is example for a constitutive relation. We will come across one more when we discuss species balance. What is the units of K? If you take this equation, left hand side we have heat flux which is watt per meter squared, right hand side we have temperature gradient, and if you divide these two we will get watt per meter Kelvin. Okay. That is a unit of thermal conductivity. K can take on a wide range of values. It could be as low as 0.01 for gases up to 1000 for pure metals, okay, very wide range. And the thermal conductivity is a function of temperature and pressure. This figure from Welty and others from the book Fundamentals of Momentum, Heat and Mass Transfer shows the effect of temperature on thermal conductivity for solids, liquids and gases. For the gases, thermal conductivity increases with temperature, but for solids and liquids you see different trends. It could be increasing, it could be decreasing. Similarly, here also it could be increasing, decreasing, so different trends are possible. Let us have a very quick application of the Fourier's law of heat conduction. We use the Fourier's law of heat conduction in a heat flux sensor to measure the heat flux. Okay. Let us read the example. A thin film heat flux sensor is used to measure heat flux incident on a surface, and that is what is shown here. We have a surface here and heat flux is incident on the surface. A thin barrier, and that is shown here, thickness 0.2 mm of polyimide of thermal conductivity K equal to 0.25 watt per meter Kelvin is is attached to the surface. The temperature difference measured across the barrier is 5 degrees. For example, let us say you have a thermocouple here, you measure that temperature, you put a thermocouple here, you measure the temperature here. So, the temperature difference measured across the barrier is 5 degrees centigrade, determine the heat flux incident on the surface. Okay. So, let us use the Fourier's law of heat conduction. Let us use in terms of magnitude, that is what we want. So, I have expressed as just K dou T by dou y. In terms of difference, K delta T by delta y, we are given the value of K, the temperature difference, the thickness of the barrier. So, if we substitute, a simple substitution will give us 6250 watts per meter squared. That is the heat flux incident on the surface. I would like to mention that by using this expression, what we have done is indirectly measured heat flux. Though it says measure heat flux, it is not direct measurement. We have measured only temperature difference directly, and using Fourier's law of heat conduction we have found out or determined in the heat flux, which means we are measuring heat flux indirectly. Similar to our molecular momentum flux, velocity gradient is measurable, molecular momentum flux is not measurable. Similarly, the viscous stress also is not measurable. Similarly, here also heat flux is not measurable, only temperature gradients are measurable. So, this example also illustrates that. Okay, now, let us compare the one dimensional form of Newton's law of viscosity and the Fourier's law of heat conduction and see whether they are similar or not similar. Okay. Let us write down the Newton's law of viscosity, the one dimensional form, and for this we are going to interpret tau as molecular momentum flux. Okay. That is why we have a minus sign here. Okay. Let us write down the Fourier's law of heat conduction. once again the one dimensional case, and here we have written tau y x is equal to minus mu dou v x by dou y, and here we have written q y is equal to minus k dou t by dou y. Now, if you look at them, they are similar expressions, both of them expresses a flux in terms of a gradient of a measurable variable with a negative sign. So, left hand side in both the cases we have flux, molecular momentum flux, heat flux, right hand side velocity gradient, temperature gradient. In both the cases the coefficient of proportionality is a physical property characteristic of the material, the first case viscosity, second case thermal conductivity. So, based on this we can conclude that the molecular transport of momentum and heat are mathematically analogous. Not alone that, from a physical picture also they are analogous, that is what is shown here. For this discussion we will take the two parallel plates case, and for the present discussion we will consider the space between the two plates to be filled with gas, that will help us for easier discussion, and that is why it is shown in green color. Now, what happens in the case of momentum transport, molecular momentum transport? The molecules in this layer will have a higher velocity, higher x momentum, molecules in this layer will have a lower velocity, lower x momentum, and hence x momentum is transported in the y direction. Molecular x momentum is transported in the y direction because of the random motion of the molecules. Analogously here the molecules here will have a higher temperature, which means they have a higher internal energy. The molecules here will have a lower temperature, lower internal energy. Now, because of molecular motion, internal energy gets transported from the molecules in this layer to molecules in the layer above, and that is what we call as heat. So, in the first case molecular momentum flux, x molecular momentum flux gets transported in the y direction from a region of high velocity to a region of low velocity. In the second case heat flux gets transported from a region of higher temperature to a region of lower temperature. So, in terms of molecular mechanism also they are analogous. Now, having said they are analogous, let us compare the 3 dimensional Newton's law of viscosity and the Fourier's law of heat conduction. Okay. So, let us write down the Newton's law of viscosity. Of course, now we have to write 6 equations. There are 6 components of the molecular momentum flux tensor. So, we will have to write all the 6 equations for the Newton's law of viscosity. Once again we are interpreting in terms of molecular momentum flux. And objective is to find out whether they are similar or not, just like we did for the one dimensional case. Now, let us write down the Fourier's law of heat conduction, once again the 3 dimensional version. Now, we will have to write 3 equations, one for each direction. Okay. Now, very clear, even the way I started, the way in which I explained, they are not analogous. I said write 6 equations there, write 3 equations here, they are not analogous, they are different. Why is it so? Why is it so? Heat, as we know, is a scalar, but molecular momentum is a vector. Heat flux is a vector, molecular momentum flux is a tensor. So, there is one tensorial order of difference. So, in this sense molecular transport of momentum and heat are not mathematically analogous. So, the strict analogy is applicable only for the simpler one dimensional case. If you go to the 3 dimensional case, the mathematical analogy breaks down. In one case you have scalar and then vector, for the case of heat, for the case of momentum it is vector and then tensor. So, they are not mathematically analogous. Okay, so let us go back to our differential energy balance equation where we left a few slides back. The left hand side in terms of the substantial derivative of temperature, right hand side was in terms of the components of the heat flux vector, and that is where we said we need to close the system of equations, which means that we need to express the heat flux in terms of temperature. We know it is now in terms of temperature gradient, and that is what we have done now using the Fourier's law of heat conduction. So, let us write down the Fourier's law of heat conduction, the 3 dimensional version, and then we will have to just substitute in the above equation, and the system of equation now becomes closed. So, let us do that. Left hand side is same, and we have a minus sign here, you have a minus sign here. So, it becomes positive here, and I have dou by dou x of q x, q x is k dou t by dou x, similarly y direction, similarly z direction, and this term appears as such here. What is the big change that has happened? In this equation it was in terms of heat flux, unmeasurable, unknown, but now I have expressed that in terms of the temperature, which is a measurable variable. So, this equation is also a differential energy balance equation for temperature, where the right hand side now has been completely expressed in terms of measurables. Otherwise, only these were the measurables here, these were not measurables, but now every term here is in terms of measurables.